Yes.
Cool, you can start now, I guess. So it's been a decent amount of time.
Okay.
And yeah, this is this is a educational meet as part of the inter-college CP camp. So it's taken by Anurudh Peduri, and he's a CFGM and a 2020 World finalist. So okay, if there's resound and stuff, I'll mute myself, so it'll just be him talking. So yeah, he'll be taking this meet on geometry.
Thanks. Yeah. Hello. Hello, everyone. Today I wanted to talk a little bit about how to approach geometry problems in CP and some tips and tricks on how to go about that. I think in the announcement that was shared before, there was a small blog post that uh, contained a few things that I had collected when I gave a similar meet about a year or so ago. And yeah, like I'll mostly cover something similar and maybe a problem or two at the end to put things together. Yeah, please feel free to ask questions in the live ask link, and which I'll keep monitoring during the stream. So let's get started. Uh, Maybe the first thing I want to start with is there are multiple ways of uh, like we'll come to how like later on in this meet we'll come to how to approach solving geometry problems, but there are multiple ways of modeling geometry problems computationally that like people choose based on what they have used before. I think the most common way I've seen is using coordinate geometry, where people keep track of like x and y coordinates, or in three dimensions x, y, z coordinates, and then they know like you write line equations, for instance. Uh, so yeah, you keep track of points using the coordinates, so on, and then let's say for lines, you use equations like in one of two standard forms usually, but of course more forms are also there. And now, like if you want to do more complex manipulations, for instance, given two lines, find their intersection, people have expressions that compute them based on these coefficients. And this is what I've seen most people do, especially at the start. And although this is technically correct, and it's not a very convenient uh, formalism to deal with geometry, purely because you have to deal with all these numbers, these coefficients that you have as if they're completely independent, and there is no easy way to yeah like write concise equations that help you keep track of like how you're solving the problem. I think one of the biggest issues people face, I mean, or two of the biggest problems people face with geometry is precision and division by zero. For precision, yeah, like in if you approach problems with a very ad hoc way, like you might be tempted to just make everything floating points because you might have divisions here and there. And it, okay, there's a question, but it's not really relevant to this meet. So I'm going to ignore that. Yeah, so you want to test, like you might end up with divisions, and yeah, forcing yourself to use floating points might lead to more errors because it's hard to exactly keep track of floating points and stuff like that. The other issue is yeah, division by zero, and with coordinate geometry, that can, especially when you have a lot of random terms floating around, it's really hard to analyze when they become zero, and you'll have a lot of edge cases that you have to deal with, which is pretty common in geometry implementations. But like with a few tricks and some a disciplined approach, you can try to avoid most of them, or at least keep track of exactly why they happen, and make sure you minimize the number of edge cases that you have to deal with. And each edge case is also very logical when you look at the code. So the alternate approach, which I will discuss today and think people might be familiar with, is using vector geometry, which is a very nice formalism that helps us. write more concise equations. So points are just some vectors in some space, and usually this could, uh, when you convert it back to the coordinate system, they would be like, uh, in simple terms, you can write them as like in a matrix column, let's say. So this is just the representation of the vector. But later on, when we use these objects, we will just deal with the abstract object and not their respective coordinates. And yeah, like now, I think most of you are familiar with what a equation for a line looks like. Here, for instance, I think the y equals mx plus c form is something like this, where the slope is m and this intercept is given by the value c, or the other form that is ax plus by plus c equals 0, which uh, yeah, I actually don't remember, but I think you can figure out what these 2 points are, which should be something like minus c by b and minus c by a or something, minus c by b and minus c by a, and this gives you the line. So in uh, vector geometry, one standard way of defining a line is if you have a point P on it, and if you have any unit vector uh, u cap that, sorry, any vector u bar that goes on the line, then any other point on this line can be written as, uh, let's call this P naught. Any other point P can be written as P naught plus lambda u, where lambda is a arbitrary real number. So here, when we talk about objects, the basic objects that we have are points, and anything else is usually just a collection of points. So a line is just a collection of points that are given by p naught plus lambda u. It's a linear equation with the parameter lambda, which as you vary, lambda equals 0 gives you the starting point, and then positive on the right side and negative on the left side in the diagram I've drawn here. So yeah, like now, if you want to talk about any arbitrary point on the line, it would have this form that we've written down here. Um, yeah, maybe let's just spend a few more minutes constructing few other simple objects. And because there is no way for me to, uh, yeah, I don't think there's no way for me to get answers from the crowd, so I'll just continue. Let's say now we have a line, and how would you model a line segment between 2 points? So if you have 2 points A and B in the space, how do you model an arbitrary point P that lies somewhere here? So you can usually think of this as, let's say this, like we parameterize by a number lambda, where lambda belongs to the reals, then this point can be written as uh, lambda A plus 1 minus lambda B. But now because we want this point P to lie inside that, we instead choose uh, lambda to be some number between 0 and 1, some real number between 0 and 1. So for lambda equals 0, you get the point, sorry, mm, maybe, yeah, sorry. Yeah, so when lambda is 0, you get the like you get the point A. So maybe to be more precise, this P prime is actually a function of lambda. It's not a single point. So yeah, when lambda equals 0, you get A, and when lambda equals 1, you get the point B, and everything in between is given by this. So you can now parameterize a point on a line segment the same way. And similarly, if you instead choose, instead, if lambda was a real number, then this P lambda would be a line, would be the entire line that basically passes through the points A and B. And now you can also parameterize a ray, like by the same logic, you can parameterize a ray, let's say that starts at A and goes towards B. by just choosing lambda to be positive numbers. I think, sorry, lambda to be maybe less than one in this case because I think I messed up what I chose my lambda to be. Yeah, so you can in general parameterize arbitrary types of like variants of lines using a linear form like this. And maybe something that's not very commonly known is how to parameterize a circle because it's not very obvious. So let's say I have my center of my circle at C, and I want to parameterize this point that lies on it using some, uh, yeah, like let's say P is a point on the circle, and I want to say that, yeah, like this thing lies at, like has a radius R, so circle of radius R. So one way to do that is by just saying that the length of this vector is R, so that is actually P minus C dot P minus C is R square, right? So now if C was the origin, then this is just P dot P equals R square. And in this case, yeah, in general, if it's not, you'll get an equation of this form. P dot C plus C plus R square. So yeah, like you have a quadratic equation here in terms of P, where the multiplication here is the dot product. And usually like here, P is the point that we're trying to parameterize, and C is something that's given to you. So you can write the equation of a circle, or you can basically parameterize an arbitrary point. Sorry, you can define an arbitrary point on a circle by this constraint. And another way to do it is by just you can choose the angle here, and then you could set the coordinates by using a rotation by that angle. But yeah, like I won't go into that now because I don't think I'll use it in today's meeting at least. But yeah, now maybe what else did I want to cover in basics of geometry? Yes, okay. Maybe now talk a little bit about simple operations. One, usually you want to, like, you're given some problem where you have some geometric space. Let's say it's a two-dimensional space. You're given some objects in that and you want to manipulate them. A few of the most common things that you might want to do are just like rotate the space. Let's say you want to pre-process it so that some points lie on the axis, which makes your life easier, or you want to reflect things uh, about a certain line or about a certain point, and we'll try to just write down how these equations look like. So let's say you want to rotate a point about the for now, let's say we want to rotate a point about the origin. So I have a point P and I want to rotate it by an angle of theta to get a new point P prime. Then I can think of P prime as some rotation action. So this is an operator, and in in simple cases like here will only deal with Euclidean spaces. So this ends up being an n cross n matrix for n-dimensional space. And one there are standard ways to compute. For instance, for r theta for two-dimensional spaces is two-dimensional spaces is given by I think cos theta minus sine theta cos theta. Oh, so this performs the rotation. And the nice thing is because it's matrix algebra, like vector algebra, this is going to be satisfy a bunch of nice properties to simplify uh, like this. Like you can, this is linear, for instance. So if you want to talk about r theta of A plus B. This is going to be r theta of A plus r theta of B. Yeah, like you can use such properties to simplify expressions that you have. And also, if you have a neatly written geometry template which gives you access to these objects, you can just manipulate and compute the final objects very easily. So, like one standard operation you might want to do is rotation. So you just build the rotation operator and then just apply it on your points. Um, Similarly, you can do more things, which I don't want to really go into detail, but yeah, let's say you can do reflections about a point, about a line, and like in 3D, you can even do them about a plane. And in general, you can model different operations like this. What else do we usually like to do? Let's say find intersections of lines. Maybe for this, I'll just give uh, specify a brief comment, which is remember that we parameterized. If you have two lines, then let's say they're given by a plus lambda u, and another line which is b plus let's say gamma v, and this point is basically some value of lambda comma gamma such that a plus lambda u equals b plus gamma v. Okay, so if you're able to find these values of lambda and gamma or just one of them, then you have found the point of intersection. We'll look at how to compute this, but because we've parameterized them using these two real numbers, now the computation purely reduces to finding just these two numbers, which is somehow exactly what you would do in any other formalism, but we'll just see in a minute how this thing makes it very easy with some very clean vector geometric operations. But maybe other things that you could do are same intersections, but for line segments or rays or for circles and like or between circle and line, which are usually useful things to do when you want to compute. These are standard things that we standard pieces of information that we might want to obtain from our geometric input. What else could one be interested in? Maybe I should look at the KSETL notebook. Yeah, you might want to compute things like and you can do all these things in 3D as well, where circles become spheres, or you can even think of circles on planes and plane intersections. Um, and yeah, like line intersections in 3D or skew lines, testing for them. You can do a lot of different operations. Yeah, and I think if anybody has wait, thing is wrong with the live ask, no, I think there's no questions yet. So now, like, I'll describe this particular operation, or rather, this trying to compute line intersections. Obviously, I don't expect anybody to actually sit and code up these exact formulas when during the contest, but they should be part of your template. But it's always nice to know exactly how to compute them and code them up once, or at least pick them from a template and know like where they are and when they work. So maybe solve, let's try to solve this equation. So I want to somehow, there are two parameters in this, lambda and gamma. And it would have been nice if I just had one parameter because then I just have a nice equation which I could just compute. So I want to get rid of one of these. So what I can do is, we'll remember a few elementary operations for vectors. That is, you can do normal arithmetic, like you can add them, you can, sorry, yeah, maybe I should, you can add vectors, you can scale vectors, You can rotate them as we've discussed before and reflect and so on. These are just, the third one is not, uh, maybe. Then yeah, like geometric transformations like rotations and reflections. And we have two nice properties, the dot and cross products on vectors, or at least in Euclidean spaces, you always have them. So the dot product helps you capture if two vectors are close by, and the cross product helps you capture orthogonality. Um, so now we we know that if you cross a vector with itself, you get zero. So if I take cross v in this entire equation, I'll get something like a cross v plus lambda times u cross v equals b cross v, and the fourth term just disappears. So on rearranging this, I just get lambda is equal to b minus a cross v divided by u cross v, right? And here, I think if people have studied how to solve multilinear equations using or at least two or three variable equations at most using Kramer's rule, this exactly gives you the same thing. That is, you suppress the row and then compute the corresponding determinant of the remaining matrix, and the cross product effectively just computes the determinant. Or you can compute the cross product using a determinant. But even if you don't, like all we need to do here is if you're given these points and we have geometry template that implements subtraction and cross products, you just write up code that just does b minus a dot cross b. You divide by this. And the only case that this fails in is when the denominator is zero. So if u cross v is zero, then this fails. And what does it mean when u cross v is zero? That means that they are the same, with their vectors in the same direction. So these are parallel or coincidental lines. So if u cross v is not zero, then this gives you a unique value of lambda. And when u cross v is zero, then you can just use this equation instead, where you just have a cross v equals b cross v. So you just need to check if these two things, 2D geometry, cross product gives you a number. You just need to check if these two numbers are the same. If they are the same, that means the lines are the same. There are infinitely many solutions. You can choose any lambda you want. And if they're not the same, that means the lines are parallel. So you don't have any solutions. So in this case, what we do instead is you just have the equation b minus a cross v equals zero. You have to check this. Okay. Otherwise, you'll get unique point. Once you have lambda, you can just plug in lambda into the above equation, and then you can compute the value of gamma. But if you only care about the point, then you can just plug in lambda into the LHS and you get the exact point as well. Um, yeah, I think that yeah, that's one way to solve this. Yeah, this problem. So usually if you have a lot of parameters in your equations, you can take cross products to eliminate some of them and get constraints on the remaining ones and hopefully use them to solve. And yeah, here, for instance, it fails when u and v are the same, in which case that just becomes an edge case that you have to deal with a little more carefully. But because you can keep track of exactly when you divide and what you divide by, and this expression, if you expand it, then it will look something like ux vy minus vx uy, which is, I mean, the exact same thing numerically, but harder to see when you just have random terms that is floating around and then add and subtract and multiply them later on. So it's nicer to have more compact terms when you do derivations that you can keep track of when things fail. Like for instance, division by zero errors here when u cross v becomes zero. So this is how you solve the line intersection problem. Now you might be wondering, does this work for line segment intersection? And it does. You don't need to do anything extra. The code is exactly the same. You just need to check if the final value of lambda you obtain is between 0 and 1. So Uh, that's just a bonus with no extra implementation required. If lambda and gamma lie in 0, 1, we have, uh, or rather, maybe I think okay, not this lambda. Like I think yeah, if the line is given by this thing where it's b is a plus u, this case, or in general, like you can just write down the same equation using the other inputs that we had before and then do the same thing. And the only thing that varies is yeah, like here, for instance, this is lambda is the parameter, which is here. Lambda is between 0 and 1, we have like line segment intersection. So there's nothing extra to be done to independently check a lot of constraints or anything. Like the vector geometry just gives us a cleaner way to write what we have and parameterize things with as few things as possible. And yeah, like parameters also carry a little more intrinsic intuitive meaning that you can that can help you keep track of what objects that you're dealing with as you go ahead and solve your problem. So you can get line segment intersection, ray intersection, everything based on if you just know what range of parameters apply to your particular problem, then you automatically just need to add an extra test for the output, and you get these things for free. Okay. Yeah, if you have any questions during the meet, please ask them on the live ask channel. I think there's no other channel that's being monitored. Um, yeah, I'll just stop for 30 seconds before I continue. Okay, maybe maybe I'll briefly discuss some other interesting computation one can do, slightly more complicated than line intersection. Okay, maybe I'll take a risk and try to do compute line circle intersection, which I've forgotten the details for, but hopefully should be able to figure them out.
You have a question, by the way.
Sorry. U cross V is a vector, right? How do you divide? Ah, sorry. I think I didn't clarify. So in two-dimensional space, U cross V is not a vector. It's actually just a number. And yeah, in 3D geometry, U cross V gives you another vector, but there taking the cross will not suffice. Okay, maybe I discuss that first. 3D line intersections, which I think should take up enough time. So first, how do you model a 3D line in vector geometry? Fortunately, it's exactly the same. If you have a line, there's a point A on it, and there's a direction vector U on it, then you can always again think of a point P parameterized by lambda as P lambda equals A plus lambda U. Can you explain the bonus part again? Okay, I think, anyways, as you lag from YouTube, I hope that that's not affecting things too much. Yeah, so for the bonus thing that I said here is just that if you had a line segment that was defined by the points A and A plus U, and the equation is effectively given by A plus lambda U for this, then any point that lies between these two is parameterized by lambda being 0 to 1. So if you solve for, if you just assume that they're fully lines and you find the intersection, now the only thing you need to check for is if the intersection point lies inside the segment or outside. And that check is just checking if lambda is between 0 and 1. That gives you the point inside. And if you instead chose a different way to parameterize your line segment, then you'll have maybe some other parameter, let's say alpha. And yeah, like you will know the constraints for, on alpha for when the point lies inside the line segment. So using that constraint, you can just compute line intersection first, and then just check if the output point lies inside the line or not. Yeah, I mean there are other ways to even check if a point lies uh, on a line segment. For instance, uh, maybe how do I add a page in between? Yeah. So if you have 2 points A and B, they're given a point P, and you want to see if uh, P lies in the line segment AB. That's effective to checking these some of these distances. You just check if this triangle is degenerate. So you just check if the distance between A and B is the same as the distance between A and P plus the distance between B and P, where basically subtracting two vectors gives you the distance vector between them. So one can just check. In general, this is a more general technique. In the previous case, we already know the point lies on the line, so we just need to check something simpler. But yeah, one like if you have a problem where you need to just check if point lies on a segment, then you can use this to check that. And yeah, like if you want to check if the point lies on a line, then uh, you just need to check that these two directions are the same in the sense they lie on the same thing, like same or opposite. So you just check B minus A, and you cross that with P minus A, and you check. So this is P lies in line AB, the same as this. Just checking if this cross product is zero. And I mean, one can simplify this by expanding the terms, but doesn't really matter. Yeah. So now maybe to talk about 3D lines, the the beauty of this is that an object looks exactly the same in any dimensional space. If you have a line, the equation and how it looks is identical independent of what dimension you're dealing with. So the line equation will always look the same. And of course, we don't like, let's say you want to talk about a plane equation that doesn't really occur in 2D, but only occurs in 3D. But if you hypothetically were given a problem which deals with a four-dimensional or five-dimensional Euclidean space, the equation of a 2D plane in that space would look identical to an equation of a 2D plane in a three-dimensional space. And this makes things a lot nicer to deal with because you don't need to figure out like weirder equations. Because I think in coordinate geometry, I don't remember how, I think we have something like this for a line equation. I I hope I'm not messing something up. Or maybe this is for a plane. No, no, no. Plane equation looks like a line equation. So in coordinate geometry, when you have the same object but in different dimensional spaces, you have varying like completely different equations, which make it hard for us to intuitively keep track of like what we're trying to compute. Um, but yeah, in vector geometry, you have this ability to exactly keep track of what is happening. So the equation for a line or parameterized point on a line is going to be always this, like given a point and a vector given a point on the line and a direction vector, it's always a plus lambda u. So now we want to we're given two lines. Let's say we're given another line which is parameterized by q gamma, which is some b plus gamma v, and I want to find where they intersect. And what happens when they intersect? I just have to equate these 2 points and find the values of lambda. And notice that till now I've not done anything different. Like I pretended that they're just lines, and it doesn't matter like how large of a space they lie in. And now the only thing that gets tricky is cross products are only well defined for two-dimensional and three-dimensional spaces, and so that makes it a little tricky to deal with. So I'll show you two approaches. One is, let's say you have three-dimensional spaces, then you can still take the same thing. So you'll let's say I cross it with v bar, and this term will disappear anyway v cross v. But now these other things that you have here are going to be vectors. So this basically says that lambda times u cross v exactly equals the vector b minus a cross v. Okay, so now you just have this nice vector equation. And unfortunately, you can't just divide by u cross v because that's not a number anymore, it's a vector. But you can just think of this as like lambda times some vector a equals some other vector b. So now you just need to check if a and b are actually just in the same direction. And lambda is just a scaling factor between them. And it's very easy to compute lambda here. Maybe I write this above. So let's say you have some equation like this where in capital A, capital B are some vectors, and you would just want to find the value of lambda, or at least tell if lambda is the same. So one thing you can do is you can first compute lambda to be norm of B by norm of A. And I'm hoping that, again, if A is a null vector here, which is A is basically U cross V, if A is a null vector, that means U and V are exactly in the same direction. So these are parallel or like equal lines, in which case you can just check if B minus A cross V is a zero vector to find out if they're the same line or if they're just parallel lines. And if they're not parallel lines, in the three-dimensional case, you get this extra thing where there can be two lines that are not parallel and still don't intersect, and these are called skew lines. And for that, once you find this lambda and then you plug it back here, the only thing that lambda can do is scale A. It cannot fix the direction of A if A and B are actually different. So if A and B here are actually in different directions, then this value of lambda that you compute is not going to solve the equation. And then you get, like if this doesn't work, then you get skew lines. So if U cross V is zero, then you get parallel or coincidental lines. And if they're not, then you proceed to find out lambda and you plug it in by dividing the norms. And if it doesn't match, you have skew lines. And if they do match, then you actually have the point of intersection because you just know the value of lambda, you just plug it in into p lambda, and then you have the exact point of intersection. So as you derive your equations, you naturally get all the edge cases out at ease whenever you have to make a choice. Like whenever you choose to divide by something, you get a natural edge case when that is zero. And because we have these things written down in a very concise way, we know exactly what they also mean. So we can keep intuitive track of them as we proceed to solve the problem. And it's always a good idea to think about like what these random constraints mean. Like u cross v equals zero, one could just ignore it and pretend that okay, like it's just some number being zero, or in this case, it's just a vector being the null vector. And you can pretend, okay, like I don't know what that means, but I'll just write an edge case for it. But it's always nice to actually think about why that edge case is occurring or what it signifies in the problem, because it might help you actually figure out something uh, like better to unwrap the solution at the end. Yeah, for 3D line intersection, it's almost the same procedure, except that we get this cross products, the end which are vectors. So you just need a little more trickery to finally solve them and extract the value of lambda correctly. one, sorry, if you think, okay, one more thing, so one other approach you can take. So this is approach one. Another approach you can take is that dot products always work. So any arbitrary Euclidean space defines, or any arbitrary like vector space within a product. So any arbitrary Euclidean space always defines a dot product. So whatever the dimension of the vectors are. So if you have a set of equations that were only derived using vector arithmetic and dot products and not cross products, then you can be sure that this thing that you've derived works for any dimensional space. And I think that is signified in one of the practice problems that I've shared, which is also there in, I think it was a problem from the ICPC Kanpur regionals from 2019. Uh, I I hope it's there in the VJudge that will be shared later. Yeah, I think it's there. Yeah. So in which you're given lines in like a 10 power 5 dimensional space, and you have to effectively find some sort of intersections between them. And the beauty is, if you derive your intersection formulas using only dot products, then you just don't need to do anything extra. You just copy paste the same thing and it works whatever the dimensional space is. You just need to change what your vectors are. They'll just have more numbers, and your dot products will be multiplying all those numbers pairwise, and your rotation matrices will be like larger matrices, but the equations and the templates would work like magic, unlike coordinate geometry where you have to sit and figure out them. So dot products always work in any dimensional space. So maybe let's pick out the equation again and see what we can do without using cross products. So one thing I can use is I can use this identity that u dot u is just the norm of u square, which is just a number. So this is a number. In fact, it's always a positive number, which may not be useful, but yeah, it's a number. So yeah, I think one small comment I wanted to make, when you when you write down equations, I think it's always a good idea to keep track of what types objects have, and especially as programmers, I think you already are used to this concept of keeping track of types of objects when you declare them in your programs. So yeah, like this would be like a vector in the space, this would be a vector in the space, and the dot actually gives you a real number, a positive real. So I think it's a good thing to keep track of the objects so you know that you're not making mistakes. Like for instance, in 3D line intersection, the cross product gives you a vector, so you can't just divide by it carelessly, because there is no meaning to dividing by a vector. So yeah, now I'm going to try to solve this set of equations using um, only dot products. So let's say um, I take like dot with u. So I get a dot u plus lambda u dot u equals b dot u plus gamma p dot u, right? So now all of these are numbers, and you just have a linear equation in lambda and gamma. And similarly, if I take the dot with v, I'll get another equation in lambda and gamma. And now you can just solve for these two and find the values. I'm trying to see if there is a quick way to explain how to solve this. So this is one option. You can just pick any two vectors and take the dot product so that you get two equations. The only problem is if you end up getting a set of uh, insufficient equations, which is like linearly dependent equation. So you can also choose some vector u perp that is perpendicular to u. And now if you take the dot product, So somehow, let's say you know how to construct this vector, which in 2D you can do it pretty easily, like constructing something that's orthogonal. And in general, you can always find, like for any vector, like you can always find something that's orthogonal to it. And if you have that, then taking this dot product with that eliminates the value of lambda. So it just gives you this. So if you're able to find this vector, then we can again go back to the same equation, but just with dot products. And now again, like this equation, you'll have to end up dividing by this term. You'll divide by this term. So when this is zero, uh, you may or may not have a solution. That means the lines are parallel. So basically, if V and U perpendicular, V and a vector perpendicular to U have a dot product of zero, that means V is also perpendicular to U perpendicular. Then you may not have a solution, like, or they might be the same line, because yeah. And note that in 2D spaces, this means that U and V are in the same direction, but in high dimensional space, this does not mean that, like, because U perpendicular is just some vector. So it just means that U and V lie in the subspace that's perpendicular, which is like an n minus one dimensional subspace. And they could still be actually different directions. Yeah, in which case you just check if these two things are equal. So yeah, if you derive your like equations or you derive a way to solve your problem only using dot products, then it automatically generalizes to any higher dimensional space. Yeah, maybe I won't really talk about circular intersection because I took up a lot of time. I think I'll spend the next 15-20 minutes discussing one problem, which was from our first week's contest, the B problem. Uh, Let me quickly open it up on my computer. So yeah, like in this problem, what were we given? Like we just uh, segment A. So you're given two segments, two line segments. So now let's write down the problem. So this is 470038B. So you're given two line segments, A and B, and you're given a vector V. And you're asked to check if uh, along this direction V, whether A blocks the view of B. That is, if I pick some line, like starting from A along this direction V. Uh, Sorry, let's hope I'm not messing up. In other words, there is a point on A such that if you move in the direction of A, you hit. If you move in the direction of B, you hit this. Yeah. So it just asks you to find if you move in this direction, starting from any point in some point in A, if you hit B. And in which case you have to say, yeah, yes, they block each other. So it's like A is obstructing the view because if somebody's looking in the direction B, A is obstructing the view of B partially. And if not, if there is no such point A, then on A, then the answer to the problem is no. So how do we go about this? The first, maybe now I'll walk you through some observations that I made as I solved the problem. And I think there might be much easier ways to solve this problem as well, but this is just like my first approach to the problem that I wanted to present. So what can you think of here? Like when you look at this diagram, it seems interesting to see that if you take parallel lines to V, and if it's just in the neighborhood, it still continues hitting B if it already hits B. So it somehow seems like you can just keep moving this line up and up or down and down till you hit one of the vertices of either line segment, right? So till you hit one of these endpoints, you can keep shifting where you are. So the only thing you need to check now is if there is an obstruction, if A obstructs B, then one of its endpoints has to cause the obstruction. like one of the endpoints has to be obstructed. So either the endpoint, like because when you move this line, you can end up hitting an endpoint of A or an endpoint of B. So now this simplifies. Instead of checking for all random points here, we just need to check for these 4 points. That is, you want to see if, let's say, let's call this A1 and A2, and this B1 and B2. You want to check if, let's say, you started A1, if it hits B, if you go along B, and similarly, the same thing. So we have 4 cases. I'll just outline one of them. That is, does A1 along V obstruct B? So I'm going to just try to answer this question that I have, that if I start from A1, does it obstruct B? So what can I think of any point? Because this is a line now. So I can think of any point here along this line as some A1 plus lambda V, where lambda is some positive number, right? Because if lambda is negative, I'm actually going in the opposite direction. So that's not what I'm interested in. And here I want a ray that starts at A and goes in this direction. So I'm going to talk about some point P lambda, that is A1 plus lambda times V. And I, what do I want to check now? If I want to check if this point P actually, I mean, if there is a value of lambda such that this point ends up lying on B exactly. So I want to intersect this ray with the line segment B. So what is the line segment B? So like I have one line here, and this constraint on lambda makes it a ray, and then I have to write down the equation for the line segment B. So that can be written as, say, like B1 plus gamma times B2 minus B1, which is the direction vector on B. So this is, let's say, Q gamma. So this lies on B. So here, where this gamma actually lies in 0, 1, because if I start at 0, if I choose gamma 0, I get B1, and at gamma equals 1, it goes all the way here. So basically, gamma equals 0, 1 parameter is moving from B1 to B2. So now I have these two equations, and these are just two standard line equations that I have. And like from before, we know that we can compute their intersection. And all I do is I just plug it into the template that computes these values of lambda and gamma. So I just plug these into the like box that checks like line intersection, and then I get out the values of lambda and gamma. And now all I need to check is the constraints if lambda is in uh, is positive, and if gamma is in 0, 1. Like if I have to check if lambda is positive and gamma is 0, 1. And if it is true, then yeah, it obstructs. And this is very easy, like you don't need to do. Um, and now notice that our line intersection had some edge cases, right? Because you only get the values of lambda and gamma when, uh, because in your line intersection template, you can only return the final unique values of lambda and gamma when the lines actually intersect and not parallel. So you actually have two edge cases here. So one is like you have parallel lines, in which case you know how to deal with this, like you say, it doesn't obstruct. And then if you have the same line, so here you have to be a little careful. Uh, in the sense, now when you call the line intersection template, it actually gives you all these outputs. Like let's say you have to design it in such a way that in each of these cases it gives you the exact output. So in the third case, in the like in the case where everything works, it gives you these two values lambda and gamma. In which case, like when you in that case, you just proceed and compute, check if lambda and gamma are in the range. But if it's not, then you know when those edge cases arise, because you know that the lines are parallel and the lines are same, because you know what they actually mean, you know what they mean in the initial problem. So here, if the lines were parallel, that means that parallel but not the same, that means that yeah, like starting from A and if you go along B, and B is just something over here. So there's no issue. Like you just say no, they don't hit. But if they were the same line, they lie on the same line. Now the problem is A could be here and B could lie somewhere here, or B could lie somewhere here. And depending on these two cases, like you might have like the answer actually changes, because if B lies on the right side of A in the direction like in this direction of V, assuming V goes right, then they actually this thing actually obstructs it, but otherwise it doesn't. But then because this case is so simple to check, all you need to do is just figure out uh, where it lies. So for instance, I know V goes in this direction, and I just compute this distance, that is B1 minus A, this vector. And if I take the dot product with V, if it's in the same direction, then it's positive. So then it obstructs it. And if it's not positive, then it's behind, so it doesn't obstruct it. So you just check against both the endpoints of B by taking the dot product. And yeah, like you know that yeah, if then the same line, the dot product actually the sign of the dot product tells you where they lie, like whether it's in the direction or against the direction of the vector. So now, if you had a nice template written out which had access to line intersection and dot products and everything, then it's just a few lines of code where you just compute these like vector differences and plug in or send these two lines to that template and then get the three cases and then just analyze them independently. And yeah, like this is exactly how I solved the problem. And the only thing I made two wrong submissions, which was handling this because I needed to be a little careful. Because for instance, there's the case where B lies like this, and checking against one point is not enough. So you have to check against both endpoints, and you don't know which endpoint lies where. So you just check against both, and any one is in the right direction, then yeah, this thing obstructs B. Yeah. So now you just check this for we checked for A1. So like we're done for A1. You can just repeat the same thing for A2. Now the tricky thing is when you want to do it for B2 and B1, somehow like you want to go in the opposite direction. You don't want to check if B2 and B1, if you continue along V, it works, but you want to see if there's some point that comes from A. But the advantage is because that's equivalent to just checking if you go from B in the opposite direction. So you just do the same procedure, but you instead of using the direction vector v, you use the direction vector minus v. So you just start from b1 and b2 and see if you go in minus v if you hit the line segment A. So if you have a first function that basically checks left to right, then you just pass these like when you pass b1 and b2, you just pass minus v and A to that, and it should work right out of the box. So even though there are four cases, you just write one general checker for that, and you just brute force through these four conditions by calling the same function with these four different values. So in some sense, if I write them down, it would be like if I have a function check, so like given the starting point, and the direction I have to move in, and the final line segment, then I would basically check uh, A1 along V with line segment D. I would check A2 along V with line segment B. I would check B1 along minus V with line segment A, and B2 along minus V with line segment A. So I would just check if all of like any one of these is true. So if any one of this fits, can I show what the code looks like? Yeah, I think it would make sense. I'm just thinking what is the quickest way. Mm, How do I check my? Does it show gym submissions here?
You have to
No,
go through group, I guess.
it doesn't open here. Okay, maybe it opens here. You're not allowed to view the contest. Why? Okay, let's go to groups. What is this group called? Ah, okay, this one is open.
First one.
Oh, why is it so slow? Yeah, so I mean, I generated this code using this like CLion plugin, but ideally during ICPC you would just write these things down. So this is just uh, the geometry template from KSETL, which has all these nice operations. Uh, and yeah, so this is the function that I was referring to. Uh, maybe I should let me go to the page. Yeah, yeah. So the actual code just starts from here. Okay, I think this should work. Yeah, so this function here, this this hits function here is the one that actually checks what I've said. So it checks if you start at this point A, and if you want to see if you hit this line BL to BR if you go along direction V. So this is exactly what I described before. And we can actually implement the hits function later, but assuming that is correct, then all I need to check is, yeah, like if they hit, then it's perfectly fine. So if either of them hit, I mean, I could have put them in the same constraint. I don't know why I had two separate blocks. Yeah, like if one of these four hits works, then I'm good to go. But then there's the case where, yeah, like the edge case I mentioned before, that is, they're actually parallel. If the lines are parallel to the vector V, then I'm going to test against that. So I just check if, yeah, like this. So V cross AL minus AR basically is zero if AL minus AR, the line segment A is parallel to V. And this tests if the other line is parallel. And this tells you that both are parallel. And now you only care about the case where if these two lines are parallel, you only care about it when they coincide, like they are the same line. So if AL, BR is also parallel to V, so effectively this says that all these 4 points lie on the same line, AL, AR, BL, and BR, right? So now all I have to check is, yeah, like if I start from one of these points and end up at one of these points, so I pick a point A, which is one of the endpoints, and pick a point B, which is one of the endpoints of the other segment. And then I just want to check if the vector that goes from A to B is in the direction of V. So I just check if the dot product is positive. Okay. Sorry. What is the eraser? Yeah, sure. Yeah. Yeah. So I just check if, so this is the edge case that my hits function can't deal with. So, but otherwise, what does my hits function do? This is just the line solver. Actually, I could have also just used the template for line intersection, but I don't know why I coded it myself in this case. Yeah, this is exactly the code I described to compute the line solver. So the the denominator term is going to be V cross BR minus BL, and yeah, if it's zero, then here I just say I ignore it, which I handle here, and yeah, otherwise I just continue to compute the other thing. And this thing is the additional check. So till here it just computes line intersection, and now I just check if this value uh, for t. So the equation is written down here. So maybe I'll write it again. So a plus lv equals BL plus T times BR minus BL. So this is the line. So I think I chose T as gamma when I explained before and L as lambda. So now I want to check here if T is between 0 and 1, and the corresponding derived equation for T, I believe, is numerator by denominator, num by 10. So that's, like, I just read out that equation because I did not want to divide anywhere to compute the value of T. Like I wanted to keep it all as integers. So instead of checking if, like, if I have T is equal to some alpha by beta, and I want to check if this is between 0 and 1, then I can just check if alpha is between 0 and beta when beta is positive. So I can just always make beta positive because, like, if beta was negative, I can just move the sign to alpha. So I just need to check this constraint. So no divisions involved. Yeah. So I guess here I was worried. Not I was not worried. Like I know that here I could take the values could reach up to size coordinate size power 4, which was I think 10 power 6 power 4. So it's 10 power 24. So I used int 128 to stay inside integers. But I think implementing this in Python might actually be simpler. So I would not recommend doing that because it's harder to make the rest of the code correct. But yeah, I think somebody else on the chat was discussing. Nishank was telling a solution where it only goes up to n cube, which I think is a much simpler approach. But yeah, this is just the solution I yeah, I think the key takeaway here is just that you can you just write down these objects first, and then you figure out what equations you have that you need to solve for to compute the objects of interest. Here, it's the point of intersection and a few observations. And but because you have these concise equations, it's easy for you to keep track of when what an edge case actually means. Yeah, this is the this thing is the solution for the problem modulo the template. So this thing checks if t is between 0 and 1, and this thing checks if L is actually positive. I mean, I don't even need to write it because the C code looks like C++ code looks exactly like English or math. Yep. So yeah, I think I'll stop here. This should be enough content for the meet. Please ask any questions if you have, and I'll be happy to answer them now.
Okay. I guess no more questions. Then
Yeah, I guess we can take
hello.
any other future questions offline in the Discord server at any point.
Yeah. So post this mate. I'll send a WeJudge link with some relevant problems that we can practice on, and I'll post it on both Discord and WhatsApp. But if you have any doubts related to the meet or anything, you can always ask it on the camp Discord server, and that should be fine. I guess that should be it.
Yeah,
Yeah. Then thanks a lot, Anurudh.
thanks for having me and
Yep.
bye.
Okay. Bye bye.